Okay, today we're going to talk about exponential functions. And so an exponential function is a function that can be expressed in the form f of x, so that's function notation, equals a times b to the x power. So exponential function has the variable in the exponent. So we have some things here to recognize about this. A cannot equal 0 because 0 times anything is going to be 0. That's not going to be a very interesting function. And then B either has to be greater than 0. Well, it has to be greater than 0. It can't be negative. And B cannot equal 1 because 1 to any power is just 1. So again, that's not going to be very interesting. That would just be a horizontal line. We call A the initial amount and B is the base. Why do we call B the base, do you think? Well, the base is always the number 2 taken to a power. Okay, for an exponential function, if A is equal to 1, f of x equals b to the x is what we call the elementary exponential function. So we have an example of that, f of x equals 2 to the x. If we complete a table of values, it will be pretty obvious what the function looks like. Not obvious, I should say, but then we can start to plot some of the points. So usually when we create a table of values, we're using the x values right around the origin. So let's say we use x equals -2, -1, 0, 1, and 2. Isn't that typical what you usually do when you're creating a table of values? You guys do that? All right, well, if we evaluate f of -2, we would be putting in -2 in the exponent because we're going to replace the x with whatever number is in our input here. So who knows what 2 to the -2 power is? It's 1/4. Excellent. And then if we evaluate f of -1, we're going to plug in -1 where the x is. Who can tell me what 2 to the -1 power is? It's 1/2. Good. And what about f of 0? 2 to the 0 power is equal to 1. Anything to the 0 power is equal to 1. Okay, and is this a special point, 0, 1? When you see a 0, x is 0, where do you think that point is going to live? It's the y, yes, the y-intercept. Okay, anytime you have x is 0, you always have a y-intercept when you have x is 0. Okay, and then what about if you took 2 to the first power? I ran out of space, so just mentally plug it in. 2 to the first power is 2. 2 to the second power is 4. And so if we start to graph these points, we have -2, 1/4. Well, here's 1. If I wanted to go 1/4, there's half, there's 1/4. So notice that -2, 1/4 is really close to what? It's really close to 0. Okay. What about -1, 1/2? -1, 1/2 is going to be here, halfway between 0 and 1. Then we have our y-intercept, 0, 1. We have the point 1, 2, 1, 2. Now, a lot of times you'll see plot and label as instructions. So if I label this, there's my label of the ordered pair. And then if I have 2, 4, and I want to label it 2, 4, that goes there. Can anybody predict what they think the next point is going to be? 3. If I plug in x equals 3, what would I get? 3, 8. Why 3, 8? What's 2 to the third power? F of 3 is 2 to the third power is 2 times 2 times 2, which is 8. So what we're going to see is this pattern emerging where if I connect these points, you see this is what we call exponential growth because the numbers are growing from left to right, and we call it exponential because our variables in our exponent. Let's just confirm what this looks like on our graphing calculator as well. So I'll just put the graphing calculator up. We'll go to y equals in order to graph, And to plug this in, I would need to use my exponent, so you're going to use that little up arrow, 2 to the power of x. So now you're going to put your variable in for x. If I press graph, now my graph is way zoomed out, probably from a prior lesson. So if I go zoom and wait, because it's thinking about it, zoom standard, that'll take you back to the 10 up, 10 down, 10 over, 10 over, okay? And we're kind of seeing this graph as it's happening. And that looks very, very similar. Do you guys think there's any asymptotes happening? What asymptote are you seeing? Y equals 0, because y equals 0 is the equation of the x-axis, and it looks like there's an asymptote. Think about for a minute, why does that asymptote make sense? What would happen if you were putting in smaller and smaller x values? For example, what would x2 to the negative 3 power be? If I was using the exponent, or if I was using the variable x is negative 3. 1/8. You see how that's getting really, really small? As x goes to negative infinity, you're going to get fractions, because that's what the negative exponent does, right? It says take the reciprocal. So we're getting smaller and smaller and smaller values. That's the idea of it's approaching 0, but it's never ever going to become 0. So do we have an x-intercept? If we have an asymptote, a horizontal asymptote, y equals 0, will the graph ever cross the x-axis? So will you have an x-intercept? No. Okay, let's look at the table, and we'll just confirm with our table. So these are the positive values of x. Look at what's happening to these numbers. They're getting huge, right? And that's where you see that sharp increase in the exponential growth. If you go back to the negative values of x, just scrolling through your table, you're seeing these really small decimals. In fact, how do you know that these numbers are really, really small? As x is getting negative, why are you seeing that? Are you seeing that these numbers here are really small, or do you have a question about what numbers are in your table right now? What are those numbers written in? Scientific notation. So the number 2.4 e to the negative 7 is essentially a really, really, really small number. It's less than a millionth, right? It's getting very close to 0. But we're seeing that y will never become 0 no matter what the value of x is. So therefore we don't have an x-intercept, because you are noticing that we have a horizontal asymptote. So that's basically what we're talking about here in this next section. The graph of an exponential function f of x equals b to the x. It has a y-intercept at 0, 1, and that's because b to the 0 power is equal to 1 if b does not equal 0, right? That's the reason why we have that y-intercept happening there. And then the graph approaches but does not touch the x-axis. And so therefore, this is going to produce a horizontal asymptote, which you already said is y equals 0. I made it plural, and that's why I crossed it out, because it's just one asymptote. It's not asymptotes. Okay, the graph does represent a one-to-one function. Why would you say that why would I say that it represents a one-to-one function? What can you tell about the graph? Why is it a one-to-one function? Yes, it does. It passes the horizontal line test. Passes, that's what we were talking about in the last lesson. Passes horizontal line test. Okay, if b is greater than 1, the graph increases from left to right. That's called exponential growth. And then if b is between 0 and 1, well, what kind of numbers are between 0 and 1? Fractions, right? Proper fractions. Proper fractions are between 0 and 1. So if the base is a fraction, the graph will decrease from left to right. That will be exponential decay. The domain is always negative infinity to positive infinity. Why does it make sense that the domain could be any number? There's just no restriction. I can use whatever number I want as the exponent. You can even use decimal exponents. Remember, this is all connected here. Okay, and then the range is from 0 to infinity. Why is the range from 0 to infinity, and are we including 0 or not including 0? We're not including 0, right? Whenever you have a parenthesis around the number, that means the number is not included. And why can't we include 0 in our range? That's right, because of the asymptote. The asymptote says, hey, there's a imaginary bar here, and you cannot cross it. So that's what the asymptote does, is you are not crossing that horizontal asymptote. Your graph is getting closer and closer and closer to it, but it's not crossing it. Okay, and this does relate to something that we talked about earlier in the term. On the very first day, you might have done the birthday numbers with me. Well, this same pattern that we see here, 1, 4, 2, 4, what would come next in the pattern? 8, and then 16, and then 32, and then, so what's the pattern here? The numbers are doubling. When you take 2 to the power of x, your numbers double. And so anyway, that was just something that we had learned earlier. There's another kind of famous problem. It's called the Cookie Monster problem. So the Cookie Monster comes into the kitchen and takes a cookie. See, this is a cookie right here, circular. And it eats half of the cookie. Okay, this is a related problem, but not exactly the same. The next day, it eats another half of what was left. So it already ate half. Half is gone, half is left. Now it's going to eat half of what's left. So what did it eat? A quarter. Okay, and then it eats half of that quarter. What's that? 1/8. And then it eats half of the 1/8. What's that? 1/16. You're seeing that similar pattern, aren't you? Right? If it eats half of the 16th, how much did it eat? Yes. And then if it eats half of that, it's getting hard to draw, right? It eats what? 1/64. So will the Cookie Monster ever eat the entire cookie? What do you think? Somebody said no. Why not? That's sort of the same thing as an asymptote, isn't it? You're seeing that it's getting smaller and smaller and smaller and smaller and smaller, but it's never truly going to go away. That's the same idea with in physics, you talk about decay of radioactive materials, right? We talk about their half-life. Well, does anybody know anything about this? Give me an example, because I don't know anything about it, actually. Half-life. What do you know about it? David, you can say it. Yeah. Okay. Get all the way there. How do you spell that? Zeno's paradox. Right, because it's like you say, you have this distance from point 0 to 1 or whatever, and you go halfway, and then you go half of that distance. Now we're 3/4 of the way because I went another fourth, and then you go half of that distance, and what's that? Getting halfway there. Is that 7/8? Because it's 1/8 left. Okay. And you go half of that distance, that's 15/16, right? It's kind of the reverse a little bit of this, but it's like, will you ever reach the wall if you go halfway? Now we're at this one right here is something like 30 seconds. Okay, and will you ever truly get there? That's kind of a summary of Zeno's paradox, right? Okay.